the biggest thing you need to know about even and odd functions is their symmetry. So an even function is symmetric over the y-axis. You could fold it in half on the y-axis and the two sides of it would match up. Okay? If you plug in a negative x, it gives you the same thing as if you plug in a positive x. Let's look at what that looks like on the graph. If I plug in 2 right here, f of 2 equals negative 3, right? That's this point right here. And it's in the table and it wants to do this weird thing where it crawls down the page. But right here at that low point, if I plug in 2, I get negative 3. Well, if I plug in negative 2, f of negative 2 also equals negative 3. It does not matter whether you plug in a positive number or a negative number for your x, you get the same y value. If you look over here, if I plug in 3, I get 2, right? F of 3 equals 2. If I plug in negative 3, f of negative 3, it also equals 2, right? So that's what it means when it says f of negative x equals f of x. So if you plug in a negative or a positive, you get the same value. Here, they give you an example of an equation, which is x to the fourth minus 8x squared plus x plus 1. Let's see, does he do this later? No. All right. So if you have an even function, all exponents are even. Now, you've got x to the fourth, x squared, those are both even. You don't have an x over here, but if I put an x with that last term, what would I have to make the exponent? 0, which is even, right? Right. Okay, so if you have a constant term on the end, it has x to the 0 with it, which is an even term. So all of the exponents are going to be even. If you have an odd function, an odd function is symmetric about the origin. And when I used to teach geometry, origin symmetry was so hard for me to explain to kids. It has to do with the distance from the origin, but the opposite direction. It's so hard for me to wrap my brain around it, but it is true that origin symmetry is the same as 180-degree rotational symmetry. Sorry, it does this weird thing where it crawls down the page when I try to write on this. So 180-degree rotational symmetry. I don't know why that says 180-degree rotational symmetry, even though it's just crawling down the page for some reason. So that means if you turn the graph upside down, it still looks the same, right? So if you rotate it 180 degrees around the axis, it looks the same. You guys can do that on your paper because you have a paper that you could turn upside down. And if you look at that graph there, it looks the same, right, whenever you turn it upside down. So this problem has the property that g of negative x equals negative g of x. What that means is if we plug in a number, and I don't have great numbers that hit grid lines so well, but let's do this. So if I do g of 2, sorry, it's crawling down the page back, worse now, I get negative 2. All right, so it's supposed to be this point right here. G of 2 is negative 2. Well, if I do g of negative 2, I will get positive 2. So that should be. So they have the opposite signs. When you plug in the positive and negative of the same x value, you'll get opposite signs for that. Okay? And in an odd function, you guessed it, all exponents are odd. So when we are asked to determine if the following polynomials are even, odd, or neither, and this would be without a calculator, so you would not be able to graph A or B. So you wouldn't be able to look at it on the graph and tell. You are just looking at the exponents of your variables. For A, you got x to the fourth, x squared. Those are both even. Any constant term, you need to put an x to the 0 with it. And 4, 2, and 0 are all even, so this one would be even. What do you guys think for B? It looks odd, but it is neither. Why would it be neither, Aiden? Because that 1 right there has an x to the 0 with it. So if you have that constant term at the end, it's not going to have an x with it, but it has to have an x to the 0. So this would be neither because of that last term. Because this term right here is okay. It's got exponent of 1. Okay, here. All right. So for C, what do you guys think? Even, odd, or neither? That one looks odd to me. If you flip it up, so if you rotate it 180 degrees, turn it upside down, it's going to look the same. What about D? Neither. It is not symmetric about the y-axis. It does have like a vertical line of symmetry, but it's not the y-axis. If you fold this in half on the y-axis, sides do not match up. It definitely does not have 180-degree rotational symmetry, because if you rotate that 180 degrees, it's going to be upside down for that. Okay, so what describes how a function blank as it moves infinitely to the right and left. So behaves, so it goes here. In other words, the end behavior is what happens to the values of y as x increases or decreases without bound. Okay, in math 3, we typically say as x approaches negative infinity, f of x approaches blank. It could be positive infinity, it could be negative infinity. It can be a number, but it's not going to be for polynomial equations. For polynomials, you're only going to get like a positive or negative infinity there. In Precal, they want us to do limit notation. Limits are actually calculus, but they want us to use limit notation to express this. So the way that we use limit notation is we put LIM, which is short for limit, and then underneath that, we're going to put what x is approaching by doing x, arrow, and then right now it's only going to be positive or negative infinity is the only thing we're going to see for these types of polynomial equations. So on the left side of the graph, x approaches negative infinity. And then you'll have f of x. Be careful not to leave off that f of x. Kids do a lot. That is what I have decided to call naked limits. You're taking the limit of nothing, right? So it's like not got anything there, so it doesn't work. So you have to put that f of x there. So this is just telling you to look at what's happening to the y values on the left side of the graph. Rather than saying as x approaches negative infinity, f of x approaches blank, what you'll see them use, the phrases you'll see them use more often in the AP Precal is as the x values decrease without bound, the y values of f of x, and then you would say increase without bound or decrease without bound. Now, approach negative infinity means that you're decreasing without bound, right? So it's just a different way to word the same thing. Same thing over here for right behavior. you'll notice that it's positive infinity instead of negative infinity, and x values increase without bound over here. This would be the same as saying as x approaches positive infinity, f of x approaches blank, whatever it is. So what it's just asking you to do is tell whether the ends of the graph go up or down, basically. So from a graph, it's very simple. We just got to get used to that limit notation. So verbally, for this graph, we would say, let's use the AP Precal preferred language here that I think you're more likely to see. As the x values decrease without bound, the y values of f of x. Now, in this case, as we go to the left of this graph, what happens to our y values? They're going up to positive infinity, right? So we would say, if we're using this language, increase without bound. Positive infinity. So this part of the sentence, as the x values decrease without bound, that tells you you're looking at the left side. And then you're looking at whether that left side, your y values go up or down. For polynomials, it's only going to be up or down. For other types of functions, you can have different things happen. But for these, it should always be up or down. Now, the limit notation I like better because it's a lot shorter. And I've done something weird again here. You would do limit as x approaches negative infinity of f of x equals, and because on the left side we are going up, up, up forever, that would be positive infinity. The part of this statement that tells you you're looking at the left side is the x approaches negative infinity right there. Yes?
How do you know if by looking at the graph of what you saw out with, like, when you said the x value decrease?
That part of the, so if they ask you for the left side of the graph, you'll just always use that phrase. Okay, because it's, if you're looking for the left side, that as you go to the left on the x-axis, your x values are decreasing. So that part right there will always be the same if they're asking you for left side. What will change is the y values of f of x either are going to increase or decrease without bound. So the first part of your statement is going to be the same every time. Same thing for your limit notation. If they ask you for the left, your limit notation is going to look like this every time. The only thing that's going to change is your answer, what it equals there. If they ask us for right hand behavior, this time we would say as the x values increase without bound. The y values of f of x. In this case, on our right-hand side, what's happening to our y values on that right-hand side? Decrease without bound. So, in a similar manner, if they're asking you for the right-hand side of the graph, let me switch colors here. The right-hand side of the graph is always going to say as the x values increase without bound, because that's where the x values are getting bigger and bigger and bigger and bigger. Right, that's the right side of the graph. For limit notation, you're going to do the limit as x approaches positive infinity of f of x. And in this case, because my graph is going down on that right side, my answer would be negative infinity. So the part of that limit statement that tells you you're looking at the right side is x approaches positive infinity. So on the x-axis, positive infinity side is going to be the right side. Okay, we are running short on time, so I'm going to skip the verbally part because I don't have a lot of time. If I am doing the left side limit statement, I would do limit as x approaches negative infinity. Make sure right here you put of f of x. Okay? You've got to have a function there. It can't be empty. So that is the same no matter what happens on my graph. On the left side of the graph, what happens to my function? Increasing. So that'd be positive infinity. And if I want to do a right side limit statement, it's going to look almost the same, but I'm going to have the limit as x approaches positive infinity of f of x. And what happens on my right side? Also positive infinity for that one as well. Okay, does that make sense? All right. Okay, let's skip. I'm going to skip the sketching of the graph. If we have time, we'll come back to it. Let's make sure we get this filled in here at the bottom. For polynomial equations, it is easiest to find the behavior of the blank side first. And that will be your right side. Now, be careful with that because a lot of times the left side limit is listed first, right? The right side goes up if the leading coefficient is positive, and down if the leading coefficient is negative. The left side goes in the same direction. Let's see. Okay. Goes in the same direction as the right if the degree is even. And it goes in the opposite direction of the right if the degree is odd. Now keep in mind here, leading coefficient, that's the number in front of your x, right? And then your degree is the exponents there, right? So our leading coefficient is the number in front, and our degree is our exponent. So if I look at example A, right, or for example 3, part A, they're wanting left and right in behavior. They want limit notation. Actually, it says limit notation is not necessary, and then they give you like this much room to write. So definitely use limit notation here. Let's use limit notation for it. For this one, my leading coefficient is positive. That tells me that the limit as x approaches positive infinity of f of x is going to equal positive infinity. Okay, so the right side goes up. If my degree is odd, then the left side will be opposite. If it's even, it'll be the same. This one is odd for my degree, so the limit as x approaches negative infinity of f of x would be the opposite, so it would be negative infinity there. Okay? So like if I look at B, I have a leading coefficient that is positive, and I have an even degree on that. So leading coefficient, think about the right. That's the limit as x approaches positive infinity of, this function's called g of x, so I want to do g of x, not f of x here. And since that leading coefficient is positive, I'll get a positive number there, or a positive answer there. The left is going to be the same, so make sure you do limit as x approaches negative infinity of g of x equals, and that one will be positive infinity as well. I need you to look over at your neighbor's paper. Make sure they don't have this written. Limit as x approaches infinity equals infinity. Okay, what's wrong with that? Well, let's say they wrote it on the right side. It is the right side. But what's wrong with it? There's no function that you're doing the limit of. There's nothing there. If you do this on your paper, I'm going to draw this fellow right here. I like to draw him. And say, naked limits. He's in shock at the nudity of the limits there and is upset. So look at your neighbor's paper. Make sure they don't have any naked limits. We don't want any limit nudity on your papers. Okay. We're going to skip around just a little bit here. Well, let's look at C. C is not multiplied out, but raising x plus 3 to the 6th power would be a terrible feat to have to accomplish. We are going to learn a shortcut on it in this class later, but it's still not fun. So let's imagine multiplying it out. What's the highest exponent you're going to get? 6. X to the 6th. So this is still going to be your degree, and then that negative 2 will have to get distributed to everything. So that's still going to be your leading coefficient, right? So it's not multiplied together, but you can kind of imagine what would happen if you did. So in this case, your limit as x approaches positive infinity of, it's a little tricky when they use y, because I don't like putting y there. I like using function names. What I would do is I would say negative 2x plus 3 to the 6th. I'd write the equation there. Usually I put function names, but he did do this here. And so this would be negative infinity here. And because it's an even degree, it's going to go the same direction. So as x approaches negative infinity of negative 2 times x plus 3 to the 6th, you would get negative infinity there as well.
So you're not really looking at the x, you're not looking at the y. It's going to change because of it. Like the x is always going to be positive and negative.
For the limit, your leading coefficient, so you're like imagining if you did multiply this out, this would be multiplied by your highest exponent. And so this would give you your leading coefficient. If it is negative, the right side's negative. If it is positive, the right side's positive. And then you're just, if it's even, they both go the same direction, so it's just going to match. In this case, you got an even degree, so they match. If it's odd, it'll be opposite for that. Something like F, I don't have time to do it, but what would you have to do for F? You would actually have to multiply F out before you can tell, because it is not written in standard form. If I look at like E right here, it's not in order. Here is your leading coefficient. Here is your degree. So this, I'm not going to do limit notation because of the time. The right side would be negative infinity. You got an odd degree. The left side would be positive infinity for that. Okay? And so we are out of time to go over this, but